Okay, in this video we're going to talk about Unit 11, Objective 2, and this time we're going to focus on the comparison test. What this test is going to do is it's going to allow us to take series that we can't use the integral test on. So we're going to say we want to use this when the integral test doesn't work. You could also use this if you just don't want to use the integral test, because we're going to be integrating with improper integrals, so we have to take the limit as b goes to infinity, and sometimes that takes a while. But there are questions that AP has asked where they make you use the integral test, so we still need to know how to do it. So we're going to use this when the integral test doesn't work. So let's go ahead and write what the comparison test is, what it means, and how we use it. So it says, suppose you have two series. First series we'll say is the sum of a sub n, and the second one we'll say is the sum of b sub n. And there's a couple of caveats here. We need both a of n and b of n to be greater than or equal to 0, and we want a of n to be less than or equal to b of n for all n. If that happens, then the following is true. 1, if the sum of b of n converges, then the sum of a of n is also going to converge. And the second thing that we can say is if a of n diverges, then b of n diverges. Now, it's important to note that these are not if and only if statements, they are if-then statements. So these do not work both ways. So if we look at option 2, we cannot say if b diverges, then a diverges. We don't know that. We only know that if a diverges, then b is going to diverge. So we're going to put a little star next to that second one, because we're probably not going to use that very often, because we're always going to be making b in terms of a. So what this thing means is if you were to graph the equivalent functions that are tied to your series, so we need them to be positive. Let's go ahead and graph a of n in black. So we have something that looks like this, and we'll just kind of go like that. If our second function, which we'll graph in blue, b of n, is always greater than it, always greater than the first one, as we get farther and farther towards infinity, you can kind of see that we have a horizontal asymptote on the blue function. And that horizontal asymptote appears to be 0. So as we get farther and farther and farther down the line, the terms that we're adding are getting smaller and smaller and smaller, so much so that we're going to say they turn to 0. So b is going to converge. Well, if b is always greater than a, and b converges, a is going to have to converge because it's under that blue line. And then likewise with number 2, if if a of n diverges, meaning we're not going to end up adding little pieces each time, then that's going to force b to diverge. Now again, it doesn't work the other way, because we could have, I'm going to draw a second b in red. If b of n looked like this, well, b of n is always going to be greater than that black a of n. But that black a of n looks like it converges based on my graph, and the red b of n is not going to converge. So this only works the way that it's written, it doesn't work both ways. So we can only say that B diverges if A diverges. We can't say the other way around. So really, this is only going to be useful if B of n converges. If B of n does not converge, we don't know really anything about A of n. So let's kind of see what this looks like and how we're going to use it. So a problem would look like this. Does the series from n equals 0 to infinity of 1 over 3 to the n plus n converge? So something I should have said earlier, this convergence test, much like the integral test, is not going to tell us what we converge to. It's just going to tell us that we do in fact converge. So does the sum from 0 to infinity of 1 over 3 to the n plus n converge? So whatever we're given, we're going to call that A of n. So A of n is going to be equal to 1 over 3 to the n plus n. Clearly, we can see that this is always going to be positive if we're plugging in numbers from 0 to infinity. So now we have to think about B of n. We need a function that's going to be bigger than what we're given, but still kind of be related to what we're given. Now, the trick here is we're going to try to look for p-series, or we're going to try to look for geometric series, because we can find out if those converge or diverge very quickly. So if we look at what we're given, I can kind of see a 1 over 3 to the n. I have a number to a variable exponent. That tells me I might have a geometric series that's going to be linked to this a little bit. So if we call B of n 1 over 3 to the n, that's going to be bigger than A of n every single time, because if you look at it, that plus n in your denominator of A is going to make the denominator of A bigger than the denominator of B. So if we have a bigger denominator, the actual number itself is going to be smaller. So we know for a fact that B of n is going to be greater than A of n. And we picked it in such a way that now I know B of n is a geometric series. So we just have to look at B of n. And we can rewrite that like this. Now again, we want it to the n power because we're starting at n equals 0. We don't have to say what this converges to, but we know B of n is going to converge because it's a geometric series. And the absolute value of 1/3 is less than 1. So since B of n is going to converge, therefore we know A of n also converges. So we're going to try to find a related either geometric or p-series to try to figure out if A of n is going to converge by this comparison test. So we'll call it quits on this video, and we'll see you in the next one.